Hey there, this is Mike Evans from innovativeineducation.com, and today we're going to be talking about the second elementary step in our survey of the elementary steps of organic chemistry, bimolecular substitution. And if you're a student of organic chemistry currently, or if you've been before, you've almost certainly heard of this reaction, as it's one of the most important and widely covered reactions and reaction steps in all of organic chemistry. So before we get to bimolecular substitution, it would benefit us to review a little bit about what we talked about last time in the context of proton transfer. So a generalized proton transfer is shown for you here, and what you can see is that basically it's the movement of a proton, H+, from one group to another. And so we would call both of these directions, the forward and reverse directions, proton transfers. And these are so fast that the extent of the reaction really depends on the position of equilibrium, and the position of equilibrium depends on the relative acidity of HA and HB. A lower pKa for an acid, either HA or HB, means that that acid will tend to be dissociated to a greater amount, and so whichever acid has the lower pKa, the side that's favored will be the side on which that acid is dissociated. So for instance, if HA has the lower pKa, we would favor the right-hand side of this equilibrium. Acidity depends on the stability of charges, and this is really important. So there's no need necessarily to memorize pKa's as long as you know the factors that control the stability of charges, and we've talked about those over the past couple of lectures. Right now what we're going to talk about is the second elementary step, SN2. SN2 is the bimolecular substitution step, and it's one that, as I said, a lot of students of organic chemistry have covered over the years. Part of our motivation in studying SN2 is that it's one of the earliest reactions that was discovered that can lead to carbon-carbon bond formation. Why is carbon-carbon bond formation important? Well, organic compounds are held together with C-C bonds, and so forming carbon-carbon bonds is a huge part of controlling organic chemistry in a rational way. And as a result of that, it's highly prized among organic chemists. To convince you of that, in 1912, a guy named Victor Grignard was awarded the Nobel Prize in Chemistry. And again, if you've been a student of organic chemistry, you've probably heard of the Grignard reagent, which is a carbon nucleophile, an anionic carbon that can act as a nucleophile. And it was one of the first reagents that could reliably form C-C bonds. And so now, let's turn our attention to thinking about how we can form C-C bonds and how we can envision that process occurring mechanistically. Remember, this chapter of the wiki is all about mechanisms of organic reactions and the elementary steps that comprise those mechanisms. So let's start by looking at the proton transfer step. So proton transfer step is shown here. It's the same diagram that we saw on the review slide. Now let's take the base, B, and replace that with a carbon nucleophile. That's what we've done in going from the first to the second figure here. So now, instead of a base picking off the proton, we have this carbon base still picking off the proton and generating A-. Now let's imagine converting this hydrogen into a carbon. So we've changed the electrophilic hydrogen. Remember, H+ is one of the world's best electrophiles. We've converted that to a carbon, and now we're in an all-carbon situation. At this point, the nucleophile is forming a bond to carbon, and the A group that's receiving electrons is doing so through the cleavage of an A carbon bond rather than an AH bond. And so at this point, we've formed a carbon-carbon bond, and if we were Victor Grignard in the late 1800s, we would have won the Nobel Prize for that. Hugely important process in organic chemistry, and one that continues to undergo study even to this day. So this process in which we replace a Ca bond with a bond to a new group is called substitution. And there's an elementary step that is called SN2 that corresponds to this one-step process. So notice that it's all happening in one step. The development of a new bond between, in this case, carbon and carbon, and the cleavage of the old bond between carbon and A. It's all happening in one step, and that's going to be important when we look at the definition and characteristics of the SN2 reaction. So what does SN2 stand for? Well, it's substitution. That's what the S stands for. By a nucleophile. That's the N. And the transition state is bimolecular for the rate determining step. So there's only one step here, just the substitution step, and two molecules are involved in the transition state for that step. Both the nucleophile and the electrophile are involved in the rate determining step here. We call it in because a nucleophile is attacking an electrophilic substrate. So the nucleophile is the thing doing the substituting. The new bond is from the nucleophile to the electrophile. Let's take a look at a couple of examples now of SN2. So the electrophile in these reactions is almost always carbon. And when I say electrophile, I mean the atom that is actually receiving electrons. So in this first example here, at the top, the electrophilic carbon is this one right here, receiving the electrons directly from the nucleophile. The nucleophile doesn't have to just be C-. It can be another group just as easily. Here I've shown an example where an O-, also called an alkoxide, is attacking a carbon to form a carbon-oxygen bond instead of a carbon-carbon bond. And notice that in contrast to proton transfer reactions, we have sort of a new group exhibiting sort of a different role than a nucleophile or electrophile. In a sense, it is an electrophile because it's receiving electrons via this second arrow, but it's not receiving them directly from the nucleophile. It's sort of inheriting them from its bond to the electrophilic carbon. We call that group, which corresponds to A down here in this generalized diagram, the leaving group, or LG for short. It's the group that leaves the electrophile in order to accommodate the new bond to the nucleophile. We'll see leaving groups come back again and again, so understanding their properties is going to come in handy. And what you'll see is that we can use concepts that we've already discussed, namely acidity, to evaluate how good a leaving group is and whether it's reasonable to propose a leaving group as leaving in a step that we may propose. So one of the questions you'll come up against in your studies of organic chemistry is a reaction favored thermodynamically or not? If you're interested in chemistry grad school, then you'll be asked to design and develop your own experiments, and you'll have to answer the question, is the reaction that I want to run thermodynamically favored? Because if it's not, then there's no use running the reaction in the first place. In fact, if it's not, your reaction is going to run the wrong way, right? It's going to run in the reverse direction, and you'll get no product out. So answering this question, is the reaction favored, will allow us to predict whether we can harness the chemistry that we want to in order to do useful transformations. So on this slide I have two examples, and both of these are favored, as we'll see. But don't just think because these arrows look correct that the reaction may be favored. The arrows may be logically correct and okay in terms of even orbital interactions, but that doesn't mean that they actually reflect a step that can happen thermodynamically. Remember, thermodynamics is a function of the stability of the reactants and the stability of the products and the relative difference there. It really has nothing to do, in a sense, with the arrows and how the reactants convert to the products and vice versa.